Hey, this is Horner. We're going to look at a couple different things. We're going to look at the photon model of electromagnetic waves, and then we're also going to look at the electromagnetic spectrum. So we have kind of talked a little bit about light as a wave, but a lot of evidence and experiments really let us know that electromagnetic waves can also have a particle-like nature. So we've seen that in the photoelectric effect a little bit, which we'll do more later on with. So photons are basically just particle-like components of that electromagnetic wave. So one of the experiments that indicates the particle-like behavior is just looking at a dim photograph. So if light acted like a wave, if I reduce the intensity, that should cause the image to grow dimmer, but you could still see that entire image. In actuality, dim photo only shows just a few points, okay? And when your intensity changes, you actually get to see a lot better resolution on that picture itself. So the photon model of electromagnetic waves consists of about three basic postulates. So the first one is electromagnetic waves consist of a discrete massless unit, and we call that a photon. A photon travels in a vacuum tube at about the speed of light. If it travels through air or glass or anything else like that, we actually slow light down. So you can slow light down and speed it back up to the speed of light. Every photon has an energy equal to hf. So remember, h is Planck's constant, 6.63 times 10 negative 34ths. And then we know that HF is basically just a chunk of energy, so we call that a quantum or a quantized energy. The superposition, that's just where I overlap waves of a sufficiently large number of photons, has the characteristics of a continuous electromagnetic wave, and we've kind of seen that in the last video. Here's a good quick check. It says I have a radio tower emits two 50-watt signals, one AM signal that has a frequency of 850 kilohertz and a FM signal at a frequency of 85 megahertz. So this is 850,000, this is 85 million. They want to know which signal has more photons per second, and the AM signal would have more photons every second. It's got a smaller frequency, and so therefore it's got more energy and can kick out more of those photons every second. This problem is finding the energy of a photon of visible light. So I have a 550 nanometer, remember that's 10 to the negative ninth, is the approximate average wavelength of visible light. They want to know what is the energy of a photon with that wavelength, and then they say there is a 40-watt incandescent bulb. It emits about 1 joule of visible light energy every second. So they want us to figure out what is the number of visible light photons emitted per second. So to find the frequency, remember we just said speed of light is equal to wavelength times frequency. So here frequency is speed over wavelength. So that's 3 times 10 to the 8th divided by 550 times 10 to the negative 9th. That's our nanometers. And that gives us 5.4 times 10 to the 14th hertz. Now that I know the frequency, let's go ahead and use E is equal to HF, and we get 6.63 times 10 to the negative 34th times 5.4 times 10 to the 14th hertz, and that gives us the 3.6 times 10 to the negative 19th joules. That's really small. In fact, photon energies are really very small, and we usually measure them in an eV rather than a joule. So remember, an eV is about 1.6 times 10 to the negative 19th joules. With this, we can find the photon energy by just taking that energy in joules, dividing it by 1.6 times 10 to the negative 19th, and we get a more manageable number of 2.3 eV, or electron volts. The photons are emitted by a light bulb span a large range of energies, but because light spans a range of wavelengths, the average photon corresponds to something near 550. So we can estimate that if I have 1 joule of light, that's about 3.6 times 10 to the negative 19th joules per photon. So you get about 3 times 10 to the 18th photons, and that comes at you every second. So lots of photons hitting you every time you look at a light bulb. Depending on the energy, the single photon can cause some sort of molecular transformation. So if you think about when it hits your eye, it goes back to the eye and it transmits nerve impulses, and it does that through some sort of molecular transformation. So the photon model of light is really important as we look at how electromagnetic waves interact with just regular old matter. A single photon of light with a wavelength of about 550 nanometers has that 2.3 EVs of energy. If I break the hydrogen bond between water molecules, it only requires 0.24. If I metabolize one molecule of ATP, it's about 0.32. If I break the bond of water molecules between the atoms in a water molecule, it takes a little bit more energy. It's about 4.7 times the EV. And then if I ionize a hydrogen atom, strip that electron off, it takes about 13.6 EV. So that kind of tells you how powerful a photon of light would be. This next section is on the electromagnetic spectrum. So this is a vertical diagram. So typically you might be used to seeing a horizontal view, one that goes left to right. So I could actually turn this one if I wanted to, but I like this because it shows you that things with a particle-like behavior or more of a particle-like behavior than a wave behavior at the top, and things that have a wave behavior or more at the bottom. So notice that things that are more dangerous, like gamma rays and X-rays, are up at the top, and things that are relatively inert have more of a wave-like behavior, like AM radio, FM radio. I know microwaves, you might think they're dangerous. They're actually not. It's similar to water. If I just take drops of water and hit you with those drops of water, that doesn't hurt. So just a few microwaves don't hurt you. What happens is in a microwave oven, we concentrate them. Similar to if I had a fire hose. If I hit you in the face with a fire hose, not the fire hose itself, but the water coming out of it, it'd be very hard to breathe. And that could result in some pretty bad damage. So microwaves are that same type of thing. You just have to make sure that if you do have a lot of them, that you're kind of out of the way. We do know ultraviolet rays here, these are dangerous to our skin if we get too many of them. And then we've got visible light, but if the intensity of visible light is too much, you can burn your retinas. So a lot of different things about this electromagnetic spectrum. There is a wide range of wavelengths and energies. Radio waves have wavelengths of many meters, but very low energy. Radio waves are therefore best described by Maxwell's theory of electromagnetic waves. So gamma and X-rays have very short wavelengths, and although they behave like waves, they're best described as photons. So visible light, ultraviolet, and infrared can also be described as waves or photons. Just kind of depends on our situation. An electromagnetic wave is independent of current or charge. So we do know, though, that currents or charge are needed as the source of the wave. Usually radio waves and microwaves are generally produced by the motion of a charge through an antenna. And yes, this is the antenna that you are thinking about. It could be a vertical antenna, and sometimes they are not. So here's a line. This represents the antenna. There's a dipole in which the charges are switched at a particular frequency. So when you turn on your radio and you pick up those radio waves, you're actually picking up, there's another tower somewhere that has generated these waves by taking and flipping these two charges. You have the positive on top, and then you have the negative on top, and then positive and negative. And you'll notice when you do that, you will change the direction of the electric field, and it reverses that in a frequency. The oscillation of the charges does cause the electric field to oscillate, and that creates a magnetic field, and that polarized electromagnetic wave radiates out into space. And so that's how we pick up not just radio transmissions for radio stations, but also your cell phone works the same way, does the same type of thing. Here's an antenna, and this antenna wire, you've got these two wires here sticking out of this AC source, and it will change and make this positive and negative, same thing on the bottom, and when it does that, it creates a dipole. And then that dipole, when it oscillates, creates the electric wave, which then induces a magnetic wave, magnetic field, and those two electric and magnetic fields interact to make our electromagnetic wave. And it does travel at the speed of light. So radio waves are also detected by an antenna, so we produce them by the great big tall antennas that you see outside, and then we pick them up with our smaller antennas. The electric field of a vertically polarized radio wave drives a current up and down that conductor, and it makes a potential difference that we can amplify. And for the best reception, that antenna needs to be about a quarter of the wavelength. So A radio tower has a lower frequency and it has a longer wavelength. That wavelength is usually about 300 meters, so the antenna would need to be at least 75 meters long. Instead, an AM radio detector uses a coil of wire. And because we have that coil of wire wrapped around a magnetic material, it detects the magnetic field of the radio wave. So that makes it a little bit easier to do. That changing flux of the magnetic field induces an EMF on the coil, and that is what is detected by the and amplified by the receiver. So when you have a radio receiver, you have to have some sort of antenna so that it can find that magnetic field, and then it looks at the changing flux and it makes an EMF on the coil, and that is detected and then picked up by the receiver so you can get the signal for the station. Here's a conceptual example. It says a vertically polarized AM radio wave is traveling to the right. So here's our radio wave. They want to know, how do we orient the coil and the antenna to detect the oscillating magnetic field of that wave? So we want to have that, we want that oscillating magnetic field of the wave to produce a maximum possible current in the coil. So the maximum is when that, that field is perpendicular to the magnetic field of the wave. So the plane of the coil should match the wave's plane of polarization. So it should be in the same plane, essentially, is what we want. Coil antennas are very highly directional. So if you turn an AM radio and then for the antenna in certain directions, you won't get that, and your reception will be pretty poor. Let's go on to the next one. This is radio waves and microwaves still, but we're going to talk a little bit more about microwaves and microwave ovens specifically here. In materials with no free charges, the electric fields in the radio waves and microwaves can still interact with different types of matter by exerting some sort of torque. So here's a water molecule, and the electric field can actually exert a torque on this, and it can flip it. And then when it flips down, the direction changes, and that water molecule will continue to rotate. So it starts to rotate here, and then it continues to rotate, and it can get spun up pretty quick. Because water molecules do have a large dipole, which means that there's a pretty positive and a pretty negative side, they can rotate really well in response to an electric field of microwaves in a microwave oven. So those molecules transfer all that rotational energy to the food, and that warms the food. So that's how we cook using microwave ovens. We're actually heating the food from the inside out. So let's say that you are eating a turkey for Thanksgiving. So there's our turkey, there's turkey wing. If you put it in the microwave, it's going to heat it from the inside outwards. When you roast it in an oven, the oven actually then makes that heat go from the outside in. So that's the difference between the two. The problem with a microwave oven is it's got hot and cold spots. So you'll have energy that comes in only on certain spots. When it does that, those spots get hot and the rest of the spots can be very cold. And that's kind of how a microwave oven works. Let's go on to infrared, visible, and ultraviolet light. So the oscillating charges in an antenna that produces radio waves can also are replaced by individual atoms. So now instead of using an antenna for microwave and radio waves, we now are using an individual atom. So we make an atom shake up and down, and when we do that, we produce infrared, violet, visible light, and ultraviolet light. And this portion is what we call atomic radiation. It's because of those charges bouncing up and down and making the different types of radiations. So nearly all of the radiation in our environment is thermal due to the thermal motion of the atoms and the objects. So thermal radiation is defined by a law called Stefan's law. And so if Q here is the heat radiated in a time interval delta T, by an object with a surface area A and a temperature T, that rate of heat transfer is this equation that you see here. E is what we call emissivity. It's just the measure of its efficiency of emitting electromagnetic waves. And then this little symbol here is Stefan-Boltzmann's constant, and that is just another constant number that you would use. With increasing temperature and therefore total energy, the brightness of a bulb can increase. The color of the emitted radiation will also change. So we see different temperature filaments here. So this is a very low temperature filament, a little bit higher and a little bit higher. So sometimes you'll see they'll have light bulbs rated in K values. So if you've ever done any art, they talk about the temperature of the light hitting it and how that can change the kind of the colors that you would see in a room. So that spectrum of thermal radiation does change with temperature. So here are some different things that we can see. So here the intensity of thermal radiation is a function of wavelength for an object is shown at 3 different temperatures. So at the first temperature, this really high temperature, we see that this peak is about 527 nanometers, which is kind of a greenish color. If I change the temperature of that radiation, when it hits, it actually will change it to kind of an orange, and then finally here, this one's an infrared. So the lower the temperature, the more shift we get towards the red. We call that a red shift. Increasing the temperature increases the intensities of wavelengths, so that makes the objects hotter, causes it to emit more radiation across that spectrum. The higher the temperature, then the shorter the wavelength we have. And then this can be seen in Wien's law. And that's the temperature dependence of the peak wavelength. We just take our constant here and divide it by that temperature, and that gives us the peak wavelength in nanometers. So here they want to know what are the wavelengths of peak intensity and corresponding spectral regions for radiating objects. For the normal human body temperature, 37, temperature of a filament in an incandescent lamp, which is about 1500 degrees Celsius, and the temperature in the surface of the sun, which is a whopping 5800 K. So we can use that equation 25.24, but first thing we need to do is make sure everything is in K. So body temperature would be 310 K, filament temperature is 1773 K, and then we had our other one for the sun. So here we go, we can just go ahead and find that peak wavelength for body temperature. It's about 9.4 times 10 to the third nanometers. Here for the filaments about 1600 nanometers, then only 500 nanometers for the sun. So as you get in differing intensities, you end up with shorter and shorter wavelengths. And that's pretty good. The sun's emission does peak right in the middle of the visible spectrum, and that seems pretty reasonable. Most of the energy radiated by an incandescent bulb is not visible light. Instead, most of that is infrared. So it only a 100-watt bulb only gives off a few watts of visible light, but you would never want to reach up and grab a 100-watt regular incandescent bulb because it'd be very hot, because most of that energy does not go into visible light. Instead, it goes into heat. Here's a good quick check. I have a brass plate at room temperature. It radiates 10 watts of energy. If I raise it to 600 K, that should go up all the way to 160 watts, because remember the power is proportional to the temperature to the fourth. A brass plate at room temperature does radiate 10 watts. If we double this temperature again to 600 K, the wavelength of maximum radiated intensity should then decrease, because remember that wavelength, that peak wavelength, is proportional to 1 over the temperature itself. So that one's a different question. We're actually going to skip over this problem. Let's go ahead and go on and talk just briefly about color vision. There's color sensitive cells in the retina of your eye, and they're called cones, and they have one of 3 slightly different forms of light sensitive photopigment. So it's either red, green, or blue. Oops. And so I'm going to back up here for just a second. And our color vision is a result of the 3 different responses of those cones, and so that's what gives you the millions of colors that you can see. But there's other animals like chickens, and they have more types of cones, and therefore have a really keen color vision. So ours are just red, green, and blue. X-rays and gamma rays are the last type of rays that we will talk about, our electromagnetic spectrum. These typically are high energy photons, and they are emitted by electrons, and we call those X-rays. So if the source is a nuclear process, we will call them gamma rays. So X-rays come from electrons. If I have some sort of nuclear decay like fission, or fusion, I will have gamma rays come from that. X-rays can be produced by emitting electrons and accelerating them in some sort of electric field. So this is what we would do if we want to make an X-ray tube in order to take X-rays of a patient. Those electrons make a sudden stop as they hit this metal target, and when they do that, that emits those X-ray photons. So X-rays are just photons of light, just like all the other types of electromagnetic waves. But these have a really small wavelength and really small wavelength, really high frequency, and a lot of energy. Hence why we have to be careful with them. X-rays and gamma rays are what we call ionizing radiation. The individual photons have enough energy to ionize atoms. So when that radiation hits some tissue, that can produce some cellular damage. Typically it does. And that is the end of this section.